universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all seems with one voice. It's home. Boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Hey everybody, how you doing? Tonight we're gonna take a foray down into solar eclipse avenue. Now, because it's happening tomorrow, I want to give you guys a primer, what you can expect, what to see, where and when. You know, if I know where you guys are, I can actually give you the times that you'll see it, and I'll be able to produce that. I want to say hi, of course, to Stan at Two Rivers. Jasmine's with us. Maria Wilson, hi there. Hola to you as well. ¿Cómo está usted? And we have Weather is Crazy with us. We have Tim F, of course. Michael Galea. Charles Spar's with us. Nice to see you, Charles. Yeah, so hopefully we'll just get some more folks joining us as time goes on. It's not a big deal. There will be people watching for sure. Good evening, tourists, Charles says. So what we're going to do is we're going to go through some of the basics. I was actually looking at the sun with our solar telescope today, and it's really, we're just getting it ready for looking at the sun. So we have a ways to go. Let me tell you, it's really showing the sun well, better than I remember, because I've had it for a while. So what we're going to do is we're going to use this telescope, and we're going to add a couple things to it to make it even better. And then we're going to get a camera for it and automate it and make it a remotely accessible solar telescope like the others. So we'll have SkyTour Sonoran, which will be the one that's currently active. We'll have SkyTour Benson, which we broke ground for a couple weeks ago, 3-4 weeks ago. And then we'll have SkyTour East, which will be our solar telescope. And that's just the beginning. We want SkyTour Mobile, which we're going to take on the road. And that's a whole nother thrust that Marianne, Tara, and I are doing to bring astronomy to the world. Daisy and Zoe are here with us. Hi, guys. How are you? And so let's just jump right in. You know, I know that as people join, they can pick it up. But the whole concept of solar eclipses is interesting. But I want to take you back to a little bit more detail on the sun and where we are in the universe, where our sun is in terms of its nature, its composition. So we're going to check this out right now. So you can't talk about a star like our sun without figuring out and stating where it comes from, what its spectral type is. And the spectral type is made up of a spectral class and a luminosity class. Now, what am I talking about? I'm talking about these things. This is the thing called the Hertzsprung-Russell diagram, and it was created by and discovered by Ejnar Hertzsprung and Henry Norris Russell. And these letters across the bottom correspond to a letter grade, basically a characteristic grade given to these stars. O stars are hot and blue, and they're way up here. M stars are cooler and red, and they're way down here. And the sun is right in the middle at the G25, in fact. So the luminosity class is given by a Roman letter like this. White dwarfs are luminosity class 6. Stars like our sun, fusing hydrogen into helium normally, these are class 5, or the Roman numeral V, right? The Roman numeral 5. And then the giants up here, these are luminosity class 2, 3, and 4. And then way at the top, stars like Betelgeuse and Antares, they are supergiants, and their luminosity class, in other words, brightness, luminosity's intrinsic brightness, is 1A, 1B, and there's a few other specialty exceptions. So these, when Henry Norris Russell and Ejnar Hertzsprung plotted stars on a chart based on their temperature and their color and their brightness like this, the intrinsic brightness, they discovered that there was a whole bunch of them that followed this one little path. And that one path you're seeing right there, that's called the main sequence. And the main sequence is where normal, what we call dwarfs, reside. These are stars that are fusing hydrogen into helium, which is the fundamental nucleosynthesis process that stars go through. All right? So when they stop fusing these elements, when they stop fusing hydrogen into helium, now they take a different turn. Now they might start fusing helium into carbon. And when they do that, they'll actually grow in size. And they'll stop doing the hydrogen to helium stuff, which is right in here, and they'll start doing helium into carbon, and carbon into nitrogen, oxygen, and beyond, all the way to iron that we get up in these supergiants. So the farther up they go, typically the more massive the stars are going to be. And that's kind of where we're going with this. But you'll notice that O stars are hottest and bluest, and then M stars are coolest and reddest. So you're trying to tell me, Mark, you'll say, that these big, giant, massive stars that are so big that if you put them where the sun is, they'd go all the way out to the orbit of Jupiter, like Betelgeuse or Antares. You're trying to tell me that they're cool on the outside, as cool as these little tiny stars that are only slightly larger than Jupiter? And the answer is yes. Okay, it really depends. See, we can say a star is an M. It's an M-type star. Okay, an M-type star. But now, if we say it's an say M-class star, we have to name its luminosity class to say what else it is. If it's an M5V, okay, then it's going to be a star that's fusing hydrogen into helium normally, okay? However, if it's a star anywhere on this diagram and it ends up becoming, say it's an F5, right? And say it stops fusing hydrogen into helium because it runs out of hydrogen. Now it's going to swell and get larger, and when it does that, it's going to end up in this new class, a new luminosity class, because when it swells, guess what? It gets brighter. And so we see stars that are literally as bright as 1 million times the brightness of our sun. This scale is based on the sun. So you'll see that we have a great deal of different stars out there. This is a perfect example, right? So now what happens is, if we find that in our plot here that we have a star that fits on this location, it's probably a normal star fusing hydrogen into helium like they normally do. Rascally, how you doing? So that's something to consider, all right? And when we look at white dwarfs, like in the center of the Dumbbell Nebula that we so often look at, we would actually see the white dwarf, and it's a type 6, right? But you'll notice white dwarfs can be blue and white dwarfs can be kind of yellow. It depends on their temperature. And some of the hotter ones will make big nebulas because they have lots of ultraviolet radiation. The further left you go in this diagram, more ultraviolet radiation. And the star is a lot hotter, and that ultraviolet radiation will more easily ionize the hydrogen gas and make it glow red, or ionize the oxygen atoms and make them glow green. That's typically why we see green and red in the same nebula. So all that said, this total energy output then of a star is its luminosity class, okay? And its temperature is its spectral class, okay? Now, we learned about a funny mnemonic, which is strange, but it's OBA, fine girl, kiss me. Okay, now that's what I learned, okay, when I got my degree in astronomy. However, there were actually 3 more classes. There were R, N, and S. Right now, smack. So that's kind of funny. But now we just say OBA, FGKM, because after a while you don't have to worry about trying to remember it or having something to help you remember it. So again, the sun right in the middle at 1 times the sun's luminosity is the sun. And our sun was born in a cluster at some point, and there's been a effort to try and find our solar siblings. And the solar siblings that we found, a solar sibling, we know it's one of ours. And do you know how we know that? Because this particular star, when you look at its spectrum, break the star's light up into colors, and you'll see that it has lines in it. Those lines are elements in its outer envelope that are in this outer envelope of the star that's cooler than the very, very hot center that's generating all the energy. And that particular outer envelope is relatively cool, so elements out there will absorb some of that very, very hot energy coming from the center. And what that does is puts a dark line in the spectrum. It's eating up a little bit of energy. And it shows its signature dark line. That's called an absorption spectrum. And it's because it's absorbing energy that is coming from the center of the star. So, that said, when we look at the lines in our sun, we have a varied number of lines. We have many lines in our sun spectrum, and they're in specific places for specific elements that are in the envelope of our sun. Well, the way we can find a sibling is by looking for other stars with the identical spectrum. And the reason is because when you have two identical stars, it means they formed from identical nebulae. And that's where we were looking for, was to find a sibling that was born in the same place that we were. We found one so far. So there's more for sure. So when we talk about the eclipses, all right, of this star that is our sun, there's three basic kinds. We have a partial eclipse, which looks like that. We have an annular eclipse, where the moon is just a little further from the sun, or further from the earth during an eclipse, making it a little bit smaller, so the sun can actually reach around the whole outer edge. And then we have a total eclipse, all right, and that's where the moon is bigger than the disk of the sun. Now, why do we get those different? And there's a fourth kind called a hybrid eclipse, and we won't get to that, I don't think, unless someone asks about it later. But why is this happening? Well, see, the thing about the sun is that the sun actually moves in, it moves around the galaxy, and then the Earth moves around the sun, and then around the Earth, we have the moon. And the moon goes around the Earth, not in a perfect circle. It goes around in a little bit of an ellipse. But watch carefully, because every time it goes around, okay, if this is the Earth right here, the closest approach to the Earth changes every time, okay? It migrates. You see what's happening? Okay, the closest approach is making a circle around the Earth itself. Okay, that's a precession, it's called. And that precession of that particular location, the closest approach, will mean that at some point or another, the moon is going to be at that closest approach when an eclipse occurs. And when that happens, at the closest approach, we get this kind of eclipse right here. We get the total solar eclipse, because the moon is now close to us. So it's close enough and it can block the sun. But if it's anywhere else along that path, then if it's a little further away, then we're going to get that kind, the annular, where there's a ring around the sun, okay? And that ring is because the moon is a little bit further from us, okay? So that's how that happens. And of course, the partial is when we're not in a spot to actually see any of those other two, okay? We'll talk about that. You'll see actually that. All right, so that said, okay, let's also look at some of the other things about the sun that are very important. Now, the sun, as you can imagine, is a very complex star. When I was getting my astronomy degree, one of the things we had to do was build a star. We had to build a computer model that created a star from the very core all the way out into the envelope, all the way to the surface into the corona. So we had to actually make a star and make sure that everything was working throughout the star. No small feat. That was many weeks and weeks of programming to get it to work. I got my star to work, but I think I might have had a problem with it. Might have gone prematurely might have run prematurely out of hydrogen. I can't remember. But bottom line is, it was very interesting to see how it worked. Now, in the core of the star, we have the very center. This very center is the only place where the star is performing fusion, in the very center. A lot of people don't realize that. They don't realize that, in that very center, that's the nuclear core. That's where hydrogen's being made into fused into helium. Okay, and then on the outside, moving out, we have a number of locations. Like as you move further out, these bands don't really correspond to anything here, but basically it just gets a little cooler as you go out. Now, trust me, it's still 10,000 degrees Fahrenheit at the surface. Okay, and it's still 27 million degrees in the core. Okay. About 15 million Celsius, and that's hot enough to fuse hydrogen into helium. But once, outside of that, the emission of energy from that central core moves out through all this mass in the star. And as it moves out, you can imagine that it's a very complicated journey because it's a very turbulent interior space inside the star. And on top of that, we find that our sun is also radiating outward, and there is also what's called a convection zone. You've seen a hot pot start to boil. Well, our sun has a convection zone as well. And the convection zone is this yellow area. Now, when we look at the surface of the sun, as we'll see shortly, you see the little cells of convection. And it's an area where in the middle it comes up and it goes down the sides. So stuff boils up in the center and then goes down the sides as it cools. Okay? And it's pretty cool. And I think that this is something that is very important to look at as well. So we have this radiative energy zone in this core here. We have a convection zone a little further out. And then we have the features that we see. When you put on these guys tomorrow, your eclipse glasses, right? And you look at the eclipse, you're going to be seeing this. You're going to be seeing this area right here. This is the photosphere. You're going to see sunspots. I looked at the sun today. There's actually several nice sunspots that you might be able to pick up with your eye as you look at the sun, if you have good vision and you're a good spot. Okay, so the photosphere is the relative surface of the sun. It's the area where the convection zone comes to a head, and the convection zones then spill over and go back down into the interior, where they come up and do this over and over again. Okay, and that's the photosphere. A little bit higher above the photosphere, you have another layer of hot gas that you're looking right through when you look at it with your eclipse glasses, and that's called the chromosphere. Okay, this is the chromosphere. This is an area that is in light that you can't see with your eye, but it's light that special hydrogen alpha telescopes can look at. Now what's happening is the sun is made of nearly all hydrogen gas, and it's very hot in this outside region, but the only fusion is in the center. So in the 10,000 degree Fahrenheit region of the sun out here, what's happening is the hydrogen atoms are actually ionizing. And when you look with hydrogen alpha, you see those ionized hydrogen atoms. And in many of these hydrogen alpha telescopes, they look red, okay, or orange. Usually they're black and white, and then they're colorized, okay. But this shows exactly what's going on. Now, it just misses one thing that's very important, okay? And we're going to get to the coronal hole and the prominences in just a second. But the sun is also very powerful. It has an extremely strong magnetic field. This magnetic field, okay, is utterly immense. So much so that if you ever saw a bar magnet with iron filings, you can actually see the shape of the magnetic field. That's this. The star has a north pole and a south pole, and the lines of magnetic field come out and go back in. Okay, they come out, they go back in, down here. But the sun, to complicate matters just a little more, is rotating. So as it rotates, the equator of the star moves faster than up near the poles. So those magnetic field lines near the equator get drawn out a little longer, and they eventually can wrap up on themselves. And it turns out that every 11 years or so, they wrap up on themselves enough for the sun to go through basically a tantrum where it has many, many, many sunspots. It's called a solar maximum. And then the magnetic field will alleviate itself, correct itself. And during this time, what we see is that a lot of the material on the outside of the star, this is called plasma, all right, will follow the magnetic field lines. So when you see prominences, you're seeing material that's ejected from the sun following magnetic field lines, and sometimes it'll ride right back down and go back into the sun. Really fascinating to watch. And today, there were two prominences on the sun. Now you see how this one here, this prominence, okay, if you could put that here, that on this side of the sun, that's what it looks like today. There's one here, there's one here, and there's another one down here. So the sun is pretty active today. So the prominences then are literally following the magnetic field of the sun. Right? So that's kind of how that works. Now when you put on your glasses, this is what you'll see. This is the photosphere of the sun. Now, I know it looks solid, and I know you want to say it looks solid, but it's not. If you flew into that, it would get progressively hotter and hotter and hotter. Then you're not just going to go bam and jump into and hit some photosphere. The photosphere is thousands of miles in depth, in height. So you're going to go in, and it's going to get hotter and hotter and get more and more difficult to see. Of course, you would not last very long after that. But the photosphere also has things like the sunspots. And over here you can see there's a pair of sunspots here. Right? And that's the deal with the photosphere. Now, if we colorize it, we can see the photosphere. And now you see a sunspot group that looks really cool here. This is a sunspot group. Why do we have sunspots, and what are they? Well, remember I talked about how the magnetic field gets drawn out along the equator, and sometimes those magnetic field lines can break and separate, and then they flail about and reconnect back inside the sun. Well, that creates, I won't call it a puncture, but it creates an area of great instability on the surface of the sun, and that's this. It's called a sunspot. They're known as solar storms, and they're areas where the magnetic field has been locally disrupted. And so if you look up close at these, which we will shortly, you'll see that these follow magnetic field lines very, very clearly, right? Now, there's a couple things about this that you have to understand. Okay, here's a full disk of the sun, and you can see a large group here and a bunch of other small ones. Today's sun has one that's about here and another one that's about here. So if you go out tomorrow, look there and there. The sun rotates basically once a month, so you're not going to see a whole lot of change from yesterday to today. Okay, but they go this way. So this is the photosphere of the sun. All right, a sun at the time when this was taken. But let's zoom in on a sunspot and see what that is. This Eye of Sauron that you're looking at here is really interesting because we said that the sun is 10,000 degrees at the surface. It is. It's 10,000 degrees about here, okay? But what's going on in here? Is this a hole? When I was a kid, I thought it was a hole. Then as I got older and I started reading library books, I realized, no, it's not a hole. It's actually a change in temperature. And as the sunspot, again, being a solar storm, it's an area of disruption, so heat is not transmitted as effectively in here. So what happens is it's 10,000 degrees out here, and then it starts getting cooler as it reaches the center of this storm. And in the middle, it's not 10,000 degrees, but maybe it's 9,500, 9,800. It doesn't need to be much different for it to look black against a far brighter sun. Okay? So that said, if you took this sunspot right here, you took this part and moved it off the sun, it'd glow bright red, so it was even hard to look at. But relative to the rest of the bright sun, it looks black. So it's sort of like an illusion, Now, just like with eclipses, the center of the sunspot is called the umbra, and then you have a penumbra, which is sort of like the lighter area. When we looked at this last slide, you can see it looks like it has a skirt of lighter material around the central core of dark. That's the umbra and penumbra here. And it's not the same as shadows. It's an unfortunate borrow of a term. Now, in black and white, some of the sunspots look just phenomenal. This is a large sunspot group. You can see the cooler regions in here, okay, and there. Really interesting, all right? And then you see this modeling here. See this modeled structure all the way, let me, like this here. What's this modeling here? It's modeling. It looks very strange, right? Well, what that is, we can see when we go back a slide, right? Here it is again, all right? Notice those, they look like they're little complete circles. Another little circle, another little circle. You know what that is? Remember I told you that the outer layers of the sun are a convection cell? Have lots of convection cells? Those are convection cells, individual convection cells from inside the sun. So the material is rising up in the center of this convection cell where it's hot in here, spilling over as it cools, and the outside is going to be darker for the same reason this is dark. It's getting cooler. As it gets cooler, it shows up as a darker area. All right. So relative to the brightness of the sun, it becomes very dark. And that's a convection cell that's now sinking. It's going to come up and down again. You can literally watch these. These are called granules, solar granules. You can watch them change dynamically. It takes a while. Remember, the sun is almost 1 million miles across. Okay. And things like sunspot groups, let's take a look at, say, this sunspot group again. Okay. This sunspot group is several Earths across. Okay. Several Earth diameters across. Right? This one might be 1.5 to 2 Earth diameters across. So it gives you an idea of how big the features are in the sun. All right. And it's really about 865,000 miles across the face of this. All right. So that's a fascinating, I guess, revelation if you don't know about it. Right. So looking now at this sunspot group, we're talking about a diameter of the Earth that might be about like this. So you can see how many Earths would fit across this. The solar granules, only a few, just a handful, could cover the entire Earth, sometimes only one. So even the granulation is massive, massive scales, So that's part of the photosphere, okay? The photosphere is there on the right. And then we raise up a little bit and we see the chromosphere. Now, wait a minute, Mark. How do we see a chromosphere and not see it, but see this photosphere? It comes down to understanding how light works and how your eyes work. Your eyes are able to see a range of frequencies of light. Okay? This frequency of light right here is there. You can kind of see it, but it's overwhelmed by the major brightness over here. Okay? To see this, you isolate it. You remove this, and you can see just this. This is a hydrogen alpha view of the sun. And it's actually a composite image because this right here is the prominences around the edge. And this is the chromospheric surface. To see this versus this is a slight frequency shift, ever so slightly. And so the movement in your filter to see that goes from like this to say that. It's really not much. Okay? And then you could see the prominences. They jump right out at you because as they leave the sun's surface, their light changes. And you have to alter the frequency you're looking at so that you can actually capture them and see them. Okay? So this is what you'll see with your glasses tomorrow. You can't see this really. All right? Now, at times, you can see a little whitening around the sunspots. At times. Those are called plages. Plage. So the plage might be somewhat visible, but they're generally a chromospheric entity. All right? So that's what's there. That's pretty cool. Now, the next thing is, here's a full view of the chromosphere. And you'll notice how this looks markedly red and this is orange. Okay, that's the reason that's markedly red and this is orange is because this is a composite image. Like I just mentioned, the telescope that looks at this has to have its frequency set to view just these prominences because they take a certain amount of care to see separately from the surface area here. But you'll notice something when you look at the surface of the sun. You see the little snakes riding around. What are those? That is just crazy. What are these snaky things? I think that's pretty cool. So let's let's think about that. Let's look at another image, okay, to see what we're talking about in more detail. Here's another image, and now you see there's some broad, thick shapes in here. It almost looks like dirt on the lens. But is that what it is? The answer is no, that's not what it is. You're actually seeing one of those prominences on the edge, but from above. You're seeing a prominence that's up here above the sun, but from here. And because they're cooler, as they leave the sun's surface, they get cooler, they look darker compared to the rest of the sun behind it. And to understand that, check this out. Here is an example of exactly that. Here's a prominence. Now, you'd be forgiven for thinking that that's going right off the edge of the sun. It isn't. It actually comes down here and goes through here. So there's material here that you just can't see because it's overwhelmed by this part of the chromosphere. But look at all the detail in this. See, this is what we're going to be showing you with our solar telescope when we get the solar observatory running. All right? And so this material is riding up off the sun, following magnetic field lines, which can be quite disruptive, you know. But look at that. Now, that's what we see. Why do I tell you this? Because during an eclipse, in a total solar eclipse, when the whole disk is covered, you'll see these prominences on the edge. You'll be able to catch them because the sun's brightness is covered by the moon. So you'll see them. You can see that color. You can see that color of the light with your eye. You just need to be able to have the brightness of the sun taken away so that the brightness of these prominences can be dominant. Otherwise, you'll never see it. All right? So this is cool. This is, you can almost see this in 3D here. That's what's sort of neat about this. Okay. Annie, thank you. Annie Lungden, thank you very much. I'm glad you were able to find it and join. So this is a prominence as seen from above here, and then as it reaches above the limb of the sun right here. That's pretty cool. Okay. Now here is an example of motion. This is a file that basically, if you look at the time, it starts at 2 o'clock, 1400, and it goes just to 1500, to 3 o'clock. And this is what you see in an hour's time. You might say, well, I don't see a whole lot changing. Maybe not, but that's because the features on the sun are so large that it takes hours to actually see motion. As an example, look at this object right here. All right, let me show you. Rockstar, thanks, man. So here's a sunspot group, and we're looking at it in the light of hydrogen alpha, that the chromosphere. All right, but as you look at this, right, look what's happening right here. Watch. Okay, look at that. It gets bright. Know what that is? Right there? That's a solar flare in process. And that's something that we'll be able to see with our telescope. You'll see a solar flare if there's one. This solar flare on that side of the sun is interesting because what it means is that material is coming right at us. And that's a part of what's called a coronal mass ejection. And it works like this. We see the light in 8 minutes because the light from the solar flare is leaving the sun. We see that. But the light represents light generated from these particles that are now following up behind it. And the particles are going to be slower because they're actually mass. They're not light. It's masses of particles that are coming. And those masses of particles will hit the atmosphere a day or two later, 2 or 3 days later. And when it does, it's going to be captured by our magnetic field, spiral around our poles, and create aurora borealis and aurora australis, you know, northern and southern lights. And so this is pretty cool. Now, I'm going to just let this stop here for a minute, and I'm just going to look at the chat because I know there were some questions. I want to capture some of the questions here. Let me start with this one here. There's a question from Charles. Mark, did I understand what I read? They found a yellow giant with high metal content and thought a red giant might have eaten a white dwarf. I didn't see the story yet, Charles, but I'll be happy to look at it. That'd be a fascinating thing. I don't know if a red giant could eat a white dwarf, to be honest, because the white dwarf is actually very, very sensitive to increased mass falling on its surface. And if more than, and the number is called the Chandrasekhar limit, if more than 1.44 solar masses of material falls on a white dwarf, then it's going to undergo rapid runaway fusion, and that runaway fusion would very likely destroy the white dwarf. This is what's called a Type 1a supernova, and they are basically candles for us. They tell us how far away things are because we know how bright they are. And if we see how bright they are in the sky, and knowing how intrinsically bright they are, well, we know that difference, so we can calculate their distance from that, right? So, but I'll check that out, Charles. If you have a link, please let me know. And then Doomwalker says, what do you think of Oumuamua slingshotting around the sun? Actually, I think that when Oumuamua slingshot around the sun, and I've talked to Avi Loeb about this, we've worked on some projects together, a television project. What happened was, it slingshotted around the sun because of the sun's gravity, yes. However, on the way out, it did some maneuvering which was very strange, because in the face of a gravitational well like the sun, when you have something that's going to go around the sun, it's going to probably just it's going to just do a simple gravitational whip around the sun. But if it does something different, like it redirects itself or moves in a different direction, then that captures our attention, and that's what Oumuamua did. This is why Avi said that maybe, we can't ignore the possibility, maybe this is an artificial object. And we can't, as I said, we cannot ignore the possibility. You know, and just like he, I think, I've been fighting the arrogance of science for a long time. Many of you know that of me. And I think that when we look at what happens in the universe, we can't hope to know everything. And I won't try to suggest we do. There's just a few things I know in astronomy that we can say are solid. The rest are ideas and theories. If you think about it, all we have to study the stars is the light coming from them. That's all we have, is the light coming from them. And that's it. If we had more than that, it might be a good thing, but we don't. You know? So, let's see. Anybody else have any questions here? Weather's crazy. I've heard that solar tornadoes exist. How they form and... Okay. A solar tornado kind of implies a spinning vortex like on the Earth. And because this material follows the magnetic field... let's go to this one. Okay, we look at this. Because this material follows the magnetic field, you can see that stuff draining down back to the sun, and it looks like sometimes it's swirling around, and it is. Okay, it's following a magnetic field line. But the tornado is probably 2 to 3 times bigger than the whole Earth that you're looking at. Okay, so this prominence is many Earths in size, right? Many Earths in size. Okay, so that said, I'm pretty sure that a solar tornado would not be a fun thing to be subjected to here on Earth, but luckily we never will have to worry about that. Okay, so in terms of what's really going on, this drawing badly out of scale. Obviously, if the Earth was the size of a softball, the moon is going to be at least 9 feet away. Okay, and it's going to be the size of a marble. Okay, the moon is going to be the size of a marble. So we're talking about a out of scale drawing here, but basically the principle is the same. The sun has an angular diameter. There's thickness, size to it, right? What we see in the sky, right? 1/2 degree. Well, the light from the top part of the sun comes through, hits the moon, and comes down here, right? And so that light you can see out here, but then it kind of stops there. The light from this side of the sun comes in, by the moon and does the same thing, right? So in the center, none of the light from the sun can actually get there because the moon is blocking this central part. That's totality, okay? But then the stuff around it is areas that are partially illuminated by some of the light that makes its way around at different points during the eclipse. And that is the penumbra. That's that softer area that we see. And most of us are going to be in penumbra for this eclipse. Now, if any of you are in totality, put it in the chat, and we're going to go look at a diagram that will show you exactly what to look for and when. Okay, so that said, okay, here is an eclipse, partial eclipse, time lapse taken. You can see prominences up here. This was a hydrogen alpha telescope looking at this, and there goes the moon right in front of the sun here. So that's an example. And I think that's pretty cool. Okay, so that's what's going to happen tomorrow for everybody in the United States, just to varying degrees. For the people in totality, it's going to block the sun. And when that happens, you'll see these prominences with your eyes. It's really cool. All right. No, do not use binoculars. No, do not use telescopes. Okay, do not use anything to magnify the view, because as soon as the sun starts coming back, it's going to be an instantly bright flash of light, probably coming in between lunar mountains, and that will be enough to blind you. All right. I've heard people say you can look at the sun without any protection. Well, you do it now, okay? And obviously, when you do it, you go, oh, that's too bright to look at. And that's fine. But during the totality, it may not look bright to you. As it's approaching totality, you might take the chance of looking at it. All right? Because you say it's not bright enough, and your brain may not be hit by that threshold of brightness to say, look away, it's hurting us. And you want to be careful about that. So we want to be careful about doing that, okay? Now, the path of this eclipse, we're going to show you right now, is here. This is really cool. This is the path. And but you don't get a real good idea here. And what I want to do is bring up something a little different to show you what it looks like. And that's this. This is an interactive path diagram. So when we look at this, we can see exactly where totality is going to be. And if we zoom out, okay, let me just zoom out of here. If we zoom out, okay, you can see that totality and the eclipse is only along this path. If we look at Europe over here, well, no one over here is going to see the eclipse. They're on the other side of the Earth. Remember, this is a flat map. Okay? So if you made it into a sphere, you'd see that this is totally not going to see anything. Now, for instance, you know that CERN is over here, right, in Europe. And obviously, people are talking about, oh no, CERN's going to be firing up the Large Hadron Collider during the eclipse. Well, actually, no, they're not. Okay, because the eclipse isn't even going to be there. So they may be firing it up at a certain time during the day tomorrow, but that's because that's when experiments are scheduled. They're also looking for dark matter. There's some things they're looking at, but you know what? This eclipse on our side of the planet isn't going to affect what they're doing over there. Okay, just for the record. So now, if we zoom in here, this is what's cool. We zoom in and we can find an area. Like I'm in Connecticut, so I'm actually right. I'm in Terryville, Connecticut right now as we speak. All right, and Terryville, Connecticut is right down here. And if we click on that, all right, it tells us that 92.27% of the sun is going to be covered. And it'll start at 2:12 p.m. my time. And it's going to be a max at 3:27 p.m. And then it's going to be done by 4:37 p.m. So for 2 hours, we're going to see the sun in some form of eclipse. That said, okay, That said, if you move yourself closer to the totality line, right? Like our producer Bill, for instance, okay, is in Newburgh. He's not going to see. He's going to see 92.93%, as opposed to our amount of 92%. It was 92 point something, right? So he's going to see a little bit more because he's closer to this line, right? But as you get closer, and like I said, tell me in the chat where you guys are, those that are watching, and I'll tell you what to expect and at what time, right? This is from the National Solar Observatory website, so you can go there yourself if you want to. Okay. Rockstar, yeah. CERN's going to go on online, but it really is just scheduled. It's not something that they're saying, oh, we got to do this today because we want to generate some really dangerous particles in the eclipse. Because they're not going to see the eclipse. Hey, Prophecy, how are you? Denison, Texas. Okay, cool. That's the first one I saw, Denison, Texas. Let's go look. I don't know what your weather's going to be like tomorrow. That's the other thing. Now, where is Denison? Yeah, Belgium won't see it, Mr. Django. Okay, so Arlington, Texas, and Denison, Texas. So you guys tell me where those are. Where's Arlington, Texas? Because I know that that'll be interesting. Is it near Dallas? Is it near Houston? Space Ghost is in Suffield, Connecticut. You're going to have about 92%. Yeah. All right. So let me see. We'll do one at a time here. Yeah, Space Ghost says, I'm in Connecticut, and they said when it's fully blocked, you can take off your glasses. Is this right? Well, yeah. If it's fully at totality, but, you want to put them back on as soon as it comes out of totality. But we're not going to see totality here. So it's always going to have a little sliver. I actually have a simulated view of what it's going to look like here in a minute. All right, let's check it out now. Okay, so we got people. Okay, Old School says Fort Worth. All right, I kind of know where Fort Worth is. It's right here. So for you, here it is. You're going to have 100% coverage. Lucky you-know-what. Okay, it's going to start at 12:22 p.m. your time. All right, and because it's a stream, you can refer to it and look at the times. Right, and it'll be at max at 1:41 p.m. for Fort Worth, Texas. Okay, now for other locations in Texas, again, it'll be in the stream, so you can check it out. You gotta check your weather, indeed, yeah. If we go down to southern Texas, like Fredericksburg or Austin, okay, down here, you're talking about 12:15 with a max eclipse of 135. All right, and so that gives you an idea. And then we're not going to go down into Mexico. But they just had the Edinburgh conference that just took place. And that's down here. And Edinburgh is going to be 91.28. Think about that. We're going to have more coverage here than the folks in Edinburgh, Texas. So it's interesting. They're going to be farther away from totality than we are in Connecticut. Now let's see, we had Arlington's between Dallas and Fort Worth. Oh, okay, so what I gave you before is good for Dallas and Fort Worth. It's going to be 100%, and you're going to be at 12:22 with a maximum eclipse. That's when it starts. Max eclipse is at 1:42 p.m. for you. Okay, you're going to see the corona. So when it's full totality, you take off your glasses and you're going to see it's going to flash in the sky. It's just going to become boom. You're going to see that corona. And then you're going to be able to look at it for about 4.5 minutes. And then it's going to go away and the sun will be back shortly. All right, let's see now. We have Paducah, Kentucky. James Hyatt. Let's go to Kentucky for y'all. Okay, we have Mississippi, we have Alabama, Tennessee, Kentucky, a tiny little bit of Kentucky, and this is going to be the area near Louisville here. All right, this area, let's say Louisville, 99.51%. Okay, max eclipse will be at 3:06 p.m. Okay, and then if we go north of Texas, sorry, I keep doing that. Let's go north of Texas and go to Oklahoma. I spent some time in Oklahoma City. And we'll go to Oklahoma City just first. 93.62, and we're looking at max eclipse at 1:45 p.m. for you. Again, this will be in the stream once it goes up there. Hey, Ronald's here. Okay, so now if we zoom out, I want to see Nashville, Arkansas. Yeah, okay, let's go and check that out, because I'm not sure where Nashville is, but if it's near Little Rock, then it's going to be literally, the time's not going to be that different. It's going to be 1:52 p.m. for maximum eclipse, and totality starts about a minute before that. Okay. Okay. And Mike C says Magog, Canada. I don't know where that is, but that's got to be up north here. Is it up near Montreal? I'll bet it's up here somewhere. You have to go to Canada, I'm telling you, because it's just not. It's gonna be madhouse. All right, so around Montreal, it's going to be max eclipse is about 3:27 p.m. local time. These are all local times for that location. So it starts a minute before that. All right, excellent. And Wilmington, Delaware. Let's go to Daisy and Zoe Amethyst now. If we go down to Delaware, good thing I know my map skills. If we go down to Delaware here, all right, Philadelphia, keep going, Balmer, okay, and Delaware, and I want to, let's see if we get to Wilmington here. I've been to Dover many times. Okay, I don't know exactly where Wilmington is, unless I just can't see it here. It's got to be down here. That's Dover Air Force Base. I've been there. Okay. But we'll pick something. All right, so the alternative is it's down here somewhere. I've actually never been to Wilmington, so it's in Delaware here somewhere. Well, until then, I'll just pick a generic location. It's going to be 84.57%. It really won't make that much difference, okay? But it's going to be max eclipse at 3:22, right? And up here north, I think. Oh, there's Wilmington. Sorry, 88.32 and max eclipse at 3:23. Okay, so there you go. That'll be here for you to see. Now let's see who else is in here. Thank you, James, about going north. Shreveport, Louisiana, Corey says. Let me go check it out. Corey, we're going to zoom back out here and go to Shreveport, Louisiana. Okay. And Shreveport is right there. You're very close. 98.02%. You're only a couple hours from totality there. And it's going to be 12:27 when the eclipse starts, and it's going to peak at 1:47 p.m. Right? Very cool. And let's see, anybody else got something? That red line goes through Paducah, Kentucky. All right. Yeah, I bet you it does. Here it is. There's Paducah. And it's going to be 100%. Totality starts at 2 o'clock. Maxes out at 1 or 2 o'clock. I'm sorry, maxes out at 2:01. And it's done at 2:02. That's because you're not on the green line. So you get a little less of the totality than others. But it's still totality. Okay. All right. Let's see. Anybody else got some okay, Sykesville, Maryland. Yeah, we looked at Maryland before and we noticed that Maryland is actually going to be let me do this here. What's going on? Oh, duh. Do this. Try again. Okay. All right. All right, so now we're looking at Sykesville, Maryland. Okay, southeast of Montreal for the other guy. Yeah. Let's do that Sykesville, Maryland location. Crap. Wrong key. All right. Let's do this. 1 second here. All right, so right down here. Into Delaware. We got Maryland down here. I am not sure where it is relative to Baltimore. I couldn't see Sykesville here. Is it near Annapolis by any chance? All right, well, I'm not sure where Sykesville is, but it's probably gonna, if it's along this line, it's gonna be pretty much the same. All right, so let's say here it's gonna be about 88.48% in Maryland. The eclipse duration is gonna be total of 2.5 hours here, but the max eclipse will be at 3:21 p.m. your time. Okay. All right. And let's see here. All right, let's get rid of this. And let's see, anybody else here want to know? Yeah, you know what? This is the National Solar Observatory website. It's interactive, so it doesn't have a search. I mean, we could change it to satellite view. It would be really exciting. But that's about it. Okay, but we have our... this is crazy. You know what? I got to tell you. Coming up here to Buffalo, okay, and looking at Niagara Falls. I was up at Niagara Falls when Doug Trumbull, we were doing a movie on Nikola Tesla, because Tesla was actually very important to Niagara Falls. And totality is coming through here. And it's going to be really fascinating to see what totality looks like and how many people are going to take advantage of this amazing view and get creative with totality. You know, that's going to be pretty cool. Be really neat. I was in here. So in here, it's going to be 3 minutes, 28 seconds of totality at Niagara Falls. So that's going to be pretty cool. Okay, and Izabela is saying, Mark, can you suggest online streams where we, the people, can watch? I would go to High Point Scientific, because they will actually do quite a nice job. They're actually down in South Carolina, High Point, South Carolina, I think, North Carolina. I don't want to taint them with the wrong state, but High Point does a nice job, and the last time they did a stream, I got in and actually talked. I was able to mention things to them. They're very responsive to the chatters. And I was only going in as a chatter. I didn't go in as anything. You know, I don't need to be a somebody. All right. So let's see. Again, this website is the National Solar Observatory, nso.edu. Okay, nso.edu. So go there, and you can find your town in there, and check out where the eclipse is going to pass, what time. This is an extremely nice interactive thing, and like down here in Nova Scotia, 95.48%. Yeah. But again, like I said, let's zoom out real fast just to show you. If you look at the world view here, okay, you see that the path of the eclipse literally is just this long, and that's because that's the duration of the moon's shadow passing the round Earth. Remember, the Earth's a globe. Okay? Yeah, flat earthers can't explain eclipses, but shh, don't tell them. Let them keep thinking, you know. So Ronald says, ERT Radio says, NBC will be broadcasting it. Yeah, but not without commercials, okay? So you want to get an online thing like High Point where you don't have to watch commercials. We'll be right back with totality after these words. Do you have flat hair? No, I want to see the eclipse. So that's said. So this is a great map. Again, get this map at National Solar Observatory, NSO, right? That's right there. You can see it, NSO. And NSO shows you many phenomenal features. There's a lot of stuff you can do. You can get access to data up here, okay, from historical archives, all that. You can see the Solar Observatory data, okay. There's some granules right there, along with, there's a very, very huge close-up. Quite nice, you know, quite nice. So, that said, National Solar Observatory, NSO, check it out, right? And I think you guys will be very, very happy to check it out and then to see it. Yeah, looks like mountains, but that's the sun. Yeah, cool stuff. There's your sunspot. Notice that there's stuff in here, okay? These lines are following magnetic field lines down into the sunspot or out of the sunspot. That's pretty cool. Yeah. Okay. So, going back to our presentation, you can see there's the path then. That is the path it's going to take. Now, one of the things that's interesting is you want to get a hold of your glasses. Very important. Hopefully you guys all have them. You know, hopefully you all have them. You know, Rural Chaos TV's here. Hey, hello, they're from Maine. Yeah. I used to go to Port Clyde, Maine every single summer ever since I was a child. My whole set of relatives was from there. Okay. Nice. And James Hyatt, he says, rainy today, clear tomorrow, rain Tuesday. We got lucky. Yeah, good for you, man. Okay. Roy Batty, thank you for the compliments. Ren and Stimpy. Hey, Ren, how you feeling any better? No, go away. I have socks. Are they stinky? Nice, they're stinky, the way you like it. I remember Ren and Stimpy, very funny. So your glasses, they may look silly, they may have little designs on them, okay? But you know the important part is the piece on the front, right? The mylar, very, very important. And you're going to be able to view the sun in ways that you may not have before. Now, if you want to view the sun differently and you're of a mind to do this down the line, what you could do, and I'm going to just show you my background here for now. Okay, what you could do is eventually get a telescope like this. This is the Coronado PST. Yes, it's backwards. This is the Personal Solar Telescope. This is a tuning ring right here. You turn this to view the prominences or the surface of the sun, right? This is focus, all right? And when I get the camera, it's going to go in place of this eyepiece. It's going to go down in here. And this is going to get mounted to a solar-only mount that only looks for the sun and only finds the sun. And then what we get is beautiful views of the sun. And it's a hydrogen alpha telescope. It cost $800 when I bought it, and it's actually about the same price. That hasn't changed. All right? So you get a chance to view the sun in the way that the big observatories do, and that's kind of cool. All right? So these glasses, they're actually quite nice. Now, if talking about big observatories, here's one. Now, are you familiar with Big Bear Eagles? There's a Fabi Cam, Friends of Big Bear, and it's looking in one of these tall pine trees, and you see eagles' nest, and they're showing eagles hatching and all that stuff. But in the distance, you see a lake, Big Bear Lake, and then there's a jetty, okay, which you see right here. There's the jetty coming out from the land all the way out into the lake, and that's where the observatory is. What happens is lake water has a specific way of calming the air to look at the sun. It's quite nice. Different than salt water. Okay, salt water has all kinds of particulates in the atmosphere that it raises that can rot and corrode things, but lake water, fresh water, does not. Okay, so that's pretty cool. All right, so that's Big Bear National Solar Observatory. Okay, so this is, again, the total solar eclipse, what people will see on the line, those of you that are lucky enough to be there. And this is what it will look like here in Connecticut. That's supposed to be 92%. 92% coverage. You see how bright that looks? But notice something. If you look at the other side, you can almost kind of see coronal streamers, like we saw in this image. These are coronal streamers. Okay? You'll notice there are areas where there's fewer. That's an area called a coronal hole. And the solar wind comes pouring out of there at very high speed. And coronal holes facing us can generate crazy auroras. And it's a fascinating line of study. All right? But this, you can see some coronal streamers up here You won't see prominences, all right, but you will see some potential corona, all right. But look at this is going to be really bright because until the last 1% of the sun gets blocked, you might not even notice it's an eclipse. You might just think it's a cloudy day. That's the way it works. The sun is so utterly bright, you know. So, but that's that, and in a lunar eclipse like this, the moon turns red because now the moon is not between us and the sun. It's the Earth is between the moon and the sun, and so the Earth is blocking the sun. I'm sorry, the Earth is blocking the sun from the moon. So the moon turns red because along the edge of the Earth, the moon just sees sunset. Now this is a partial lunar eclipse, so we still have some white areas, but they turn gray and then they start to get red. So you can see this is kind of the edge of the Earth here, right? The edge of the Earth is right about here. And then as we get deeper in, it gets darker red. In fact, sometimes it can get all the way down to literally looking blood red in the sky, and you might not even see it if you're looking directly at it. That's how dark red the moon can look. On this one, on January 20th of 2019, we were filming this. This is on our SkyTour live stream channel on YouTube. And at the height of the eclipse at 23:41 and 35 seconds, that's 11:41 and 35 seconds, we saw that dot. And we went into the history books because we filmed, along with only 5 other people on the entire planet, we filmed a meteor hitting the moon at the height of a lunar eclipse. And that was pretty cool. Really cool. And this was SkyTour East. I had a dome here, and the telescope that was in the dome is the one that's behind me here, that you did not see, but I will briefly show you. Okay, and so that's the one that's right there. And I can actually help you see it better just by going in and doing a highlight of it. There you go. So now you actually see the telescope right there. And that was the telescope that served as the telescope for SkyTour livestream for, a couple of years. Right? Here in my ship. So that telescope, I'm not going to install out here. I'm going to actually put the solar telescope out here instead. So this telescope may end up getting sold. So if anybody wants a telescope, I might be selling this one. Now, we'll get rid of the background, and there we go. Okay. So, that is a pretty cool night of looking at the sun. Now, if we come in here, you guys, this is the dome, by the way, that I used to have here. And you know all about our public outreach. There's the SkyTour. Actually, you probably haven't seen these. Okay. We have a Facebook site, skytourlive.com or skytourlive.org. And this is our observatory out in Arizona. This is our new SkyTour live stream all sky cam. Okay. And we can see the constellations. You can click on this little yellow dot, get the constellations. You see satellites. We actually, Izabela, who was in the chat, made a great video of an object we captured in the all sky cam. An object which effectively shouldn't be there. Now, at midnight, the sun is on the exact opposite side of the planet, right? So what you don't see at midnight are satellites because the sun is illuminating them when you see them. And you especially don't see low Earth orbiting satellites like the International Space Station. It's 252 miles up. We shouldn't see it. All right? It's up there, but the sun is not illuminating it because the ISS is in darkness. So why is it that we saw something go horizon to horizon, exceedingly bright, And the International Space Station doesn't go horizon to horizon. Satellites generally do not. So what was this? I don't know. I don't know. It's a genuine mystery. Now, it did flare at a certain point in its path as it went over us. It flared at us. And, people might be tempted to say, oh, that's a iridium flare satellite. Except it went horizon to horizon. Iridium satellites, you can't see them for that amount of time. But the iridium satellites were all deorbited in 2019, December. And so there's no more iridium flares. So it's something that people still think is up there, but they're not there anymore. They're physically not up there. So that said, we don't know what it was. And Izabela created it. And you can see that if you look what she puts the link in there. You go to our SkyTour live stream with Mark D'Antonio Facebook group. And if you... It was my flying raccoon. That's a good one, Steve. So if you go to our Facebook group, SkyTour Livestream, you can see the time-lapse video that Izabela put up there. She puts it into slow motion, so you can actually watch it traveling through the sky. I only put one frame, okay, where it's going directly overhead, and that's where it flares at us. I don't know what it was. And the only thing I can think, and this is to you, Izabela, is that, I might have mentioned this to you, it could have been a very high-flying helicopter with a spotlight. That's all I can think. Because the light was from the horizon to horizon. So I don't understand what that was. It couldn't have been a satellite, because satellites don't operate that way, especially after midnight. Especially after midnight. You know what I can do? Maybe what I can do is save people the trouble. What I'll do is I'm going to come in and do this. All right? And here's what I'll do. I'm going to go to my Facebook site, and we're going to actually show you. I'll show you this. Okay? Okay, so, warning. The solar eclipse is going to kill you. Yeah, right. All right, and let's go to my groups here. Right, and if we come down, that's the solar eclipse telescope, and that's the post I put up there. And then this is the one that Izabela did for us, and I will put it up there. I don't think you'll hear it, but well, it's very faint. Oh, there's captions. Something really cool happen, and it happens just after midnight. I think this is the one where we're going to see it, right? So it's a satellite that went over, right? But now, as it gets to past midnight now, look at that. Did you see that just went by? Isabel's going to show. I'll slow it down for you. Get illuminated. But that was a low orbiting satellite. Why would we see it when the sun is directly behind us in this image through the Earth? How could we see it? And that's pretty strange that we did see it. Really, really odd. See? So that's pretty interesting. So, again, just to make it... And it happens... just after midnight. One more time. This is the one where we're going to see it. Right, so that's a satellite that went over. All right, but now, as it gets to past midnight now, look at that. Did you see that just went by? That's something that shouldn't be there. Because after midnight, low Earth orbiting satellites don't get illuminated. I got to tell you, too, each one of these trail lengths is 20 seconds long. And we know that because it says right here, exposure 20 seconds. So for each different length of this trail, okay, this is 20 seconds, all right? And that short one was 20 seconds too, but it's going further away from you, and it's at a low, it's at an angle where it's moving away from you more than it's passing by you. So the angle and the speed, the apparent speed, is slower. Okay, and that's something that you have to remember. So right there, that's a 20-second shot too. All right, this is a 20-second shot. Right. So honestly, you have to understand that get illuminated. This doesn't make any sense. Orbiting satellite. Why would we see it when the sun is directly behind us in this image through the Earth? How could we see it? And that's pretty strange that we did see it. James Hyatt asked, how long did it take to go from horizon to horizon? Well, if you add up all the 20-second segments and you add the 1 second in between, I think Izabela said it was 4.7 minutes to go across the sky. Oh yeah, there she is. She just said it. So when you consider what this might have been, it becomes really odd. Okay, because I honestly would love to know what it was. I don't really have an idea. I don't have any idea what this was. You know. Now, could it have been a satellite? No. I've seen satellites that are very, very high in altitude, but they're not that bright, right? And they don't cover that amount of space that we saw on the screen in 20 seconds. If it's a satellite, it's moving as fast as the ISS is at 252 miles above the Earth. But if it was something that high, we wouldn't see it. Because the sun is on the other side of the Earth. The entire Earth is blocking it. So what is it? And that's the question. Yeah, pretty cool. So I want to thank Izabela for doing that video. It was really, really good. Tom, man, he said, Tron Man says, test rocket. I thought of whether it was a rocket, but keep in mind that when you see a rocket, I thought Falcon 9, all that, because we've seen them from here. Okay? Here's the thing. When a rocket's coming towards you, its exhaust is behind it. And you're not going to see that bright rocket plume, the bright rocket engine. You're not going to see it till it passes you. So when its butt is facing you, you're going to see that bright exhaust nozzle. You're not going to see it horizon to horizon. It would show up somewhere along the way where the rocket starts heading away from you and you can see the nozzle. That's when you'd see the rocket. You would not see it horizon to horizon, you know. So this was in Arizona. This is where this camera's set up. So, all right, Stan says, did you put the camera's location in the planetarium and view the day through to see what it is? I did Heavens Above, and guess what I found? Nothing. You know why? Because there's no satellites visible at that time. So Heavens Above didn't have any satellites. I did, in fact. I tried finding something immediately. Hey, Matt's here, Water Rat. What's going on, brother? Matt used to work here at FX Models, my business here. Good friend. Yeah, so if hopefully you were lurking, Matt, because I already went through the entire talk already. Yeah, so I don't get it. I don't understand. I don't understand what this could be. I just don't get what that could be. You know? Let me just move myself out of the way here for a minute. So, if you have any ideas, I'd love to hear them. I'm out of ideas. I thought a helicopter with a light, that was possibly the flare. But horizon to horizon, we wouldn't see that. I don't know what it was. I don't know what it was. Daisy and Zoe say space junk. I thought of that too. The problem is, if it was space junk, it wouldn't be white. It would actually be various shades of yellow, orange, and some white. White hot is not you're going to see things that are yellow hot, and but you're not going to see just one thing like this. You're going to see things break up and form a shower of material, like when the I hate to say it, but when the Columbia came back into the atmosphere and burned up, it didn't stay as one thing. It actually broke up into many different pieces, which you saw. And this was just one thing, you know. So, I don't know. But it was really, really odd. And again, thank you, Izabela, for doing that. That said, I'm really, really excited to think that maybe we've got a really good set of possibilities here for our telescope. We're going to have this is the West Coast one right here. The East Coast one is getting replaced by that solar telescope, which will have add-ons and additions to make it even better. And then the SkyTour Benson is going to be a telescope that will have a really, really good telescope in it that we're going to get. I want to actually get rid of this here. I want to show you something else, kind of give you an idea of where we're going, because that's kind of important maybe. So let me bring this up. All right, here we are. So first of all, looking out at our site, okay, we can see that tonight's not a good night to do it because we have clouds over there. That little bell, that's where we are. And if we run the tab, you're going to see that we have some clouds. So I was hoping I could run right into a stream tonight, but I can't. All right. And let's make sure there's not any rain in there. Didn't think so. All right. Right, so, but what I want to show you now is the mount. We're going to get two mounts this month. One is going to be for our telescope in the Sonoran, and one's going to be for the new Benson telescope. And it's going to be the Skywatcher EQ6R Pro. Okay, so this is the mount we're going to get. Right. The telescope mounts up here on top of here, so you have a big telescope up here. And this mount is robust. We're not going to get the tripod. This is going to be mounted on a big pier inside the SkyTour observatories. So we're getting two of these this month. And this mount is extremely well time tested. Oh, look, High Point. Yeah, High Point Scientific. They're gonna do a great job in the Eclipse tomorrow. So we're gonna do this. We're gonna mount our telescope that we have out there currently, and it's gonna be put on that pier that we already have out there in our observatory. Okay, and that's in here. So if you have any questions, I'd be happy to answer them for you about anything about the eclipse that I may have left out that you need some more information on. Michael Hedrick says spectral analysis. Yeah, the new one is going to do spectral analysis as well. I've got I'm going to have a grading system called a star analyzer. Anyone into astronomy knows what that is. And it's going to be in one of the filter wells, and we're going to be able to rotate in and get a spectrum. And Ronald's asking, what is the difference in the new scope setup? Well, the new scope is going to be a Celestron 11, okay, and it's going to be mounted on that Skywatcher mount. It's a very good mount, and it was originally going to be mounted on a Celestron CGX mount, but I'm saving $700 and getting a better mount. And so we're getting 2 of them to replace the telescope mount in this building with that as well. That's very important because now both telescopes in SkyTour Benson and SkyTour Sonoran are going to work identically with the same mount. This is good because it means I can use the same exact software to operate both. Carl Becker says, how do you pay for these things? Yeah, that was a good question, Carl, because we started a 501c3, and we have some donors that gave us some money, and we have some Patreon subscribers that give us money, but we're about is bringing astronomy to the masses, and there's a whole bunch of things we want to do that we cannot do yet, because we simply don't have the money, but I'm not getting paid for this, and I'm not looking for it. I'm trying to bring some really, really good education to folks that, may not have had the opportunity to see beyond the light pollution over their heads, So originally, this was all out of pocket. I built that East Coast Observatory you see right here. All that came out of my pocket through saving and, selling things, making models for the Navy, because my business, FX Models, is a model making company, a one-man shop. And I did some work for the Navy, made enough money to get telescope and dome, and very little else. I went hungry for a few weeks too, actually, so that I could get some equipment that I really needed. But don't tell anybody. And so it really ended up being quite a endeavor. And then I had to sit in that dome every night that I was doing it to do the broadcasting. And what I ended up doing was getting very cold, got sick a lot. I was out there in the dome when it was 15 degrees. And at 15 degrees in that dome, it's unforgiving. And so I ended up getting very, very chilly. But I had to be out there to move the dome, okay, so that the telescope could be looking through it. The idea was if this dome was good enough, I was going to automate it. And so that the shutter, the opening, it would be, facing wherever the telescope was pointing. The only problem was that the dome turned out to be problematic. It had flexibility that made it hard to automate. They claimed they could automate it, but a lot of people, the automatic shutter opening system didn't work as planned in a lot of people's installations, so I never got one. The dome rotation mechanism would slip, and it can't slip. It's got to absolutely know where it is at all times. So that meant I would have to engineer something way different, and the whole structure could kind of flex, and that's not good. That's not robust. So that's what led to this building here, okay? Because I made this building as a roll-off roof, and so the telescope can literally be sitting in there safe and sound, right? As you all know, you see me doing this a whole bunch of times. And when I do it, when I start it up, we find that the telescope is, ready to go. It's on its pier, and it's ready to roll, ready to show you guys the night sky. And that's actually a very important thing, And I ended up using a 1.5 horsepower garage door opener, because what you may not realize, maybe you do. Let me see if I can show this to you. Let's go here. Okay, so this is the live view of the observatory where we are right now. We can't run it, obviously, because our sky has got some clouds, but I'll show you that too. All right, so here's our interior cameras. All right, here's one camera looking down, looking up. Here is the camera looking out, and here is the handset camera. All right, this is here. All right, and so I wrote a program to control the hardware and stuff in there. That's under here, and it's an Arduino. But let's look at the night sky as it is from here now. I say night sky, you can see where we are. The stars are out, and we've got some clouds out there. All right. We get the moon elevation. It's minus 26.2 elevation, and its moon illumination 0.6. No, and that's getting a deeper elevation. Thank you, Carl. That's very kind. Well, thank you so much. That's really good. That's kind. And then we get the sunrise data right behind me here. And then we have the date and time and the exposure, 20 seconds. And the temperature is 86 on the sensor. So slightly cooler outside. Right? And so that is the current live view. We can also go in here and look at these. These are star trails. So every night we get star trails, right? Here you can see a plane crossing over last night. All right, let me move over a little bit. Okay, it's curved because the camera's it's a wide field camera. All right, so look at all the stars. They're literally overlapping. There's so many of them, right? Horizon to horizon. Look at all these stars. So this is really a cool thing. These star trails allow us to see things like this. That's a meteor right there. You can see that meteor, right? So if you don't know what I'm talking about, it's that path right there, right there. That's actually a meteor trail, okay? Another plane came through over here. This is a plane came through here. You can, wait a minute. No, that actually might be a satellite. Actually, that might be a satellite that came through at that point. All right. So I thought I saw blinking lights. Let me make sure. Yeah, no, actually those might have just been blocked by some clouds. But yeah, this was the plane. That's a bird turd. Here's the plane. You can see the belly strobe right there, right there, right there. You can see that. So that's what's going on there. And then if we back out here, you see we got star trails from a long, long time ago, way back when, every day. We also have something else. Okay, we have something called a kilogram. Now, kilograms are interesting. They're not going to mean much to you potentially, but what they do is this. If you look at them closely, they take for a swath of time during the night. Okay, here's the day, 6 in the morning all the way till 8 o'clock at night and sunset. And then into the evening hours, you actually get to see whether it was clear all night because, okay, at 9 o'clock it was clear. At 10 o'clock it was clear. It was clear all night long. All right? So if any clouds come in, you'd see some white streaks in here. It's just a snippet to kind of average the hour. And so that's what it does. And the kilogram is very helpful to give you trends for what's going on. And yes, James, those are the rotating beacons on the bottom of the plane. You're exactly right. Okay. And then, let's see here. If we go here, this is where we see all the amazing stuff. Like, here is the time lapse, okay? And I'm going to just jump ahead because daytime is boring. But there's the sun traveling across the sky. The time is racing along here. This is that was a bird that sat on our dome right there that just came and went. Very funny. Okay, and then as we move along, okay, we see bugs, and then we move into nighttime. All right. Now, as we move into nighttime, this is that time lapse where we saw that strange object. Okay. So you'll see a satellite pass through, and then you'll see another one. Okay, and that one's going to go, I think, here, followed by the other one there. And you'll see now, again, in 20-second increments. It's like you can't even stop it fast enough to see it. There it goes. Incredible. So we see these things happen on the time lapse, and it makes you go back and find them, individual frames. Wham, right through. Now you might have seen gaps. That's because there's a gap between each exposure. All right. But this thing is what you saw that Izabela then processed and showed you more of. Okay. So really cool. Michael Klages, how are you? Here's last night's time lapse. And by the way, you know what I'm going to do? And this is something that I'm just going to take as a personal project. I'm going to build a windshield wiper for the camera dome. It's going to just go sink, 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 and take care of getting rid of anything on the dome. But it also has to have a water supply. So we'll have like a little tank of water that will pump water onto the dome, and then those are all satellites you see with maybe some meteors. Okay. Isn't that pretty? Yeah, that one, see, now that's more of a satellite because you see that they start and then leave at a certain time. And before 11 o'clock, you might see that. When midnight rolls around, you shouldn't see satellites now. Okay, because now it's going to be impossible. But now as we get it later on in the evening, let's look at this. I'll show you something else. Okay. Now it's becoming 3 a.m. And what is this? Why, that is the summer Milky Way showing up. So when we look at it, you can see this is Cygnus the Swan up here. Okay, we have Vega, we have Altair, we have all these. This is the summer triangle up here. Here's Sagittarius down here. This is really a stunning Milky Way, and we're seeing it in color now. Okay, and there goes another satellite, which you expect to see at that time because it's just before dawn. Okay, so up there, the sun is illuminating it from the east. But there's the Milky Way, the Sagittarius star cloud, and the dark convoluted Milky Way up into Cygnus. And that is just beautiful. You know, and then it gets a little brighter as the day wears on here. Now, one thing we could do is once we freeze that, we can actually zoom into that and see even more detail. You can actually see nebulae from this. So this system is hugely superior to the one we used to have. It's just beyond superior. Okay, so like in here, for instance, we can actually zoom in. All right, and go even more. In fact. We'll come down. All right. And so you can see, okay, you see the Pleiades, they're behind the clouds right here. Here's Aldebaran and the Hyades right here. All right. But you don't have to take my word for that because we now have the option of just turning on all the constellations. So you can see them. And look, there's Aldebaran. This is promised. You know. There's Rigel down there. There's Betelgeuse at the top of Orion. The belt of Orion's behind the clouds, but it's there. See? There it is. Very, very cool stuff. And we're going to make this available on our website. I actually have another little mini computer right down here. And that's going to control this as a totally separate entity. And so it'll be available 24/7. All right, so we're going to do that. Stan asked from Two Rivers, Mark, is it possible that the light from Phoenix lit up that object? Nah, see, that light from Phoenix, that's 80 miles away. And this light came in from way over the horizon here. Okay? So, no, it really isn't possible. That's just crazy, isn't it? Claudio Ramos is with us. Hey there, how you doing? That's Claudio from Chile. Haven't seen you for a while, man. Hope everything is okay with you. Yeah, Jessica, how are you? Yeah, we're going to report that object and see if we can find any reason for that existence of it. Attitude Zen, what's up? How are you? How are you? Guardian Jackpot, how you doing? I don't understand your message. Spraying of plague will occur by 2 planes? Okay. Yeah, well, I don't understand, but maybe you could explain. Good, Claudia. I'm glad everything's good. Michael, it was at 12:38 and 40 seconds our time, I believe. Look, there's a plane going across the horizon right now. This is live, by the way. Yeah. I mean, I don't know if people would enjoy seeing just the all-sky cam if it's cloudy, but I'd leave it up all night, let people watch it. It's up all night anyway. So what's the difference if it's streaming it or not? You know? So I would consider doing that. But that looks like somebody squashed a fly on my glass. Amazing. Ronald says, funny how that dark lane's in line with a bird turd. Yeah, actually, on my Facebook site on SkyTour Livestream, you can see, you can clearly see the bird sitting on top of the dome. There, you can see the plane has moved from there to here, and now to there. See that? Again, 20 seconds worth of time. And each of these singular dots are the flashes of the red beacon on the plane. And if you count these dots, you're going to count 19 or 20 of them, because they flash at a 1 second interval. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. See, there are 20. No, that's a plane, Doomwalker, I was just mentioning. Starlink satellites would actually leave a trail, because they're dragging out a trail. These are momentary, instant on and off lights. They're strobes. So we see the strobes. Trust me, I've seen trails like that and said, ooh, Starlink? And I go, wait, wait, let me think. I get too excited, you know? Yeah. All right, so if I minimize this for now, or a moment anyway, I wanted to show you something, because I don't think I've ever really shown you this before. Because what I'll do is I'll just show you how the system actually functions. I can't start the telescope because we're actually, unfortunately, cloudy, so it's not going to be helpful. But what I'll do is pull this out, and pull this out. Okay, and I'll drop this down just out of the sight here. All right, and let me do this and bring that back, because sometimes I get that happening. Okay, drop this down, and there we go. Okay, so now you see our lower camera view, and you see our upper camera view here. All right, so what's going on is now that the dome is actually, the building actually has its roof on, and I tapped into the system so that I could actually just do that and open the building, so you can see the building's opening. And so the roof's sliding off. It's using an ordinary garage door opener. And I tapped into the circuit to make it actually work. Right. So now, right now, where the telescope's acclimating to the outside, you know. Mazel Shimo, how are you? Nice to see you. Bullwinkle, how you doing? I don't think I said hi to you. And Faradiba, how are you? I actually did the whole talk already, but I'm just showing folks the observatory. It's cloudy out there right now. This is what it looks like right now out there. This is a live view of our all-sky cam. See, it just changed. That's a bird turd. So we have some high clouds. But, you know, when we don't have high clouds, we will stream for several hours, actually. And I have a feeling... Yeah, Open Sesame, exactly right, Blues Traveler. I have a feeling that... you know, when people see this happening, you know, it kind of gets them excited, like it gets me excited. Of course, I'm 2,500 miles from this building. So right now, out in the middle of the desert, this roof has come off. And if anyone's over there watching, they're going, what the heck's going on? Well, the truth is, there's no one for miles, actually. This telescope system's on protected land. And you've got to, once you get off the main roads where the asphalt roads, you drive on dirt roads for 14 miles. And in that time you're gonna end up with a truck full of junk on it, let me tell you. You know, and a lot of desert pinstriping. You drive by choyas or some other cactus and you hear as it scrapes down the side of the vehicle, and you got all these horizontal scratches on the vehicle. You know. So, as we're speaking, this will actually make the telescope, you know, become acclimated, you know, and so that's the extent that we'll do tonight. I can't. You know, start it up because it's not going to make any sense to do that because it's so cloudy. But we will do this. I was going to do it tonight, but the clouds changed the story for us. So then I will now close the roof. I just can't get over the fact that that's happening 2,500 miles away. So, in any case, this building... came about courtesy of Marianne, Rob, and Tara Diulis, who supervised its building during COVID. And I couldn't go out there at that time. And I would have to say that I was going crazy while they were doing this. Because I was like, I gotta be there. But I did supervise the building from a distance, and like Max Headroom, if you ever saw that show, I was on a phone, as a picture on the phone, to the contractor. Hey, Sean, thank you. You know, thank you so much. So the bottom line is that, you know, hopefully you enjoyed our solar eclipse talk today. I want to make sure that you did. I want to show you a couple more images that we had shown you before, but I want to kind of bring them up and see if you might recognize some of our beautiful shots that we took. It's the Andromeda Galaxy, Lagoon Nebula, all taken from that telescope you just saw. This beautiful one is the Eagle Nebula. Running Man is really stunning. That's just above Orion, the Orion Nebula, which is right there. So above it is this. Yeah, so there's a lot of really interesting, very interesting stuff that this observatory here has shown us, and we're very, very happy that it's running as it is, and we're making improvements to it all the time. So once again, in summary, the total solar eclipse is tomorrow. Your times will vary. Go to the National Solar Observatory website, and they have the eclipse tracker there, and you can click on your town and see the exact time when to look. Here it's 3:26, 3:27. And for us here in Connecticut, it's going to look like this. That's an exact photo of a 93% coverage and 92%. So neat. Anyway, that's pretty cool. Black holes, sun. That's right, yeah. So don't forget these. If you have them, they are actually quite effective. All right. And if you watch long enough, you'll see this. Remember, this is the moon passing in front of the sun. Those are the prominences in the chromosphere. That's the atmosphere that's just above the photosphere that you see with these glasses. You see with the glasses, you see the photosphere. So, again, don't get your... I don't want to have you feel like you're going to see something different. This is what you're going to see. And you're going to see the moon take a bite out of that. Some of you will see this thing go away entirely. Okay, this is the photosphere in the same color as provided by the Eclipse glasses that I showed you before. Okay, and you'll see sunspots with them. And there's two sunspots. There's one fairly large one here and one fairly large one here. So by tomorrow they're going to be a little bit over here, a little bit more. Okay, but they'll be more centered on the sun actually. So those will be good for you to watch for, and you'll be able to see them if they're big enough with your glasses. And if you can't, well, don't use any binoculars. Okay. Yes, and Ronald says, he's right, even if you have clouds, you'll see dimming in the daylight. If you're in the totality zone, you'll witness the streetlights going on, which is kind of interesting. You know? So pretty cool. And remember, sunspots have an umbra and a penumbra. The umbra is the darker region and the penumbra is the lighter region. These are the magnetic field lines coursing down into the sunspot and out. Remember, it's in 3 dimensions, so this is a 3-dimensional object, which is really fascinating. And when we look at the sun, you will see with the glasses what's on the right. You'll see it in gray. But the hydrogen alpha telescope, like I showed you before, that shows you the chromosphere, which is just above the photosphere. You can see that light with your eyes, but the brightness of the sun drowns it out. But in a total solar eclipse, when the sun goes completely in front, when the moon goes completely in front of the sun, you will maybe see right around the outside edge of the sun, you might see some of the prominences like this dancing around out there. They'll be on the very edge. So look for that. Look for that. Okay. So as far as the scale of things here, and first of all, temperature, this is about 10,000 Fahrenheit here. This is a tiny bit cooler, and the prominences are a little bit cooler still. And these are prominences right here as seen from on top, because they're cooler coming out at you, right? And the proof of that is actually in looking at some of the photos. And one is this one. You can see this prominence is rising off the sun, and it's actually on the 3/4 side of the sun coming out towards you. And you can see that here. You can see that it's actually extending down into this view of the sun. Right? This stuff is much more gossamer and faint. So to see it, you have to get rid of or use a telescope that only looks at the light coming from those. All right? And the hydrogen alpha telescope is that thing. So there you go. So anyway, I'm glad that you guys were able to come here and attend and enjoy this. There's your sun. Okay? Tomorrow you'll see the photosphere with your eclipse glasses. You won't see the chromosphere If you're in totality, you might see prominences. If they come off the sun far enough, you might see one, and it's gonna look like a bright spot next to the sun. It might even have a color to it. It might look a little orange. So I think that would be pretty cool. So that's pretty neat. Hey, Louis, how you doing? No, there won't be any pole shift tomorrow. See, the internet abounds with people suggesting things that are just not true. And, you know, I'm a professional astronomer. This is what I do for a living. And I've kind of seen it all when it comes to people taking advantage of a natural phenomenon like a solar eclipse. And some of them are pretty unscrupulous, you know, but honestly, I don't think anyone needs to worry for sure about anything during the eclipse, except at the height of the eclipse. It's literally only April right now, so it could get a little chilly for that 4 minutes if you're in totality. Okay, it'll feel like when the sun goes behind a cloud. All of a sudden, it feels a little chilly, and you got to put your jacket on. You might feel that. You know, one more thing too I wanted to mention, and this is something that the folks in totality would end up seeing. The rest of us for partial won't. Have you ever heard of eclipse bands? Like rubber bands, but eclipse bands. An eclipse band is a pattern that appears when the sun is entering totality. In that last few seconds, you see these bands racing across the landscape or the big giant side. If you have an Amazon warehouse nearby and you got this big giant wall, take a look at that wall and watch what's going by, and you might actually see these bands sweeping across the face of the building as the sun gets covered. Eclipse bands have been known to make people nauseous, dizzy, but it's really not a big deal. You know, I think you should really check it out. So, in other words, keep observing, keep looking around and seeing if you can see the eclipse bands. All right? So, I am done. I think you guys got more than you needed, more than you bargained for. So, again, when you go out tomorrow to look at the eclipse, you use these guys to look at the eclipse, okay? You don't use you don't put on these guys. These are wrong things to wear for an eclipse. Regular sunglasses will not save you from going blind, because as I said, your brain may not think that it's bright enough to hurt you, but it still is. Okay, guys, that's it for me. I'm out. You guys have a good evening. Thank you so much for sticking around and hanging out with us. I hope you enjoyed it. RT Radio, it's not bad for the price of a cup of coffee. Well, I didn't even charge for a cup of coffee. Some of the folks bought everybody coffee, which was so nice of them. And thank you, guys. No problem, Matt. You're welcome for the education. The sun is a cool thing in the sky, and nobody really knows what it's all about sometimes. So you guys have a good night, and I will talk to you again. If it was clear tonight, we'd continue into a stream, but unfortunately it's not. So maybe that will be tomorrow night after the eclipse, all right? So we'll see you later, and I will talk to you later, and we'll see you on the backside the very next time. Night-night.